Let me break down chapter 5 for you. Chapter 5 is about transcendental functions. The transcendental functions are functions that can't be written as a polynomial, like a quotient of polynomials or a product of polynomials that have nothing to do with polynomials. And the transcendental functions that you know are things like f of x equals e to the x. F of x equals ln x, natural log. F of x equals, you actually know some other, any log base or any exponential base are transcendental functions. But the other main category are inverse trig functions. So these guys. Sine inverse of x. Which you'll also see written as arc sine. So inverse trig functions, exponential, and log functions are the focus of chapter 5, and what we want to do is know how to take the derivatives and integrals of all. So we want to talk about finding, deriving, and integrating with these functions. The way, I don't know. Larson has an interesting way of doing this. Jerome Larson is an interesting fellow. So the way this breaks down, 5.1 and 5.2 are all about natural log. We do derivatives and integrals that are going to involve natural log. Okay. 5.3, we don't really need, so we skip it. 5.4 is about e to the x, deriving and integrating e to the x. 5.5 is about other bases, so like 2 to the x, 3 to the x, pi to the x, exponential functions with different bases, and also log functions with different bases. So like log base 2 of x, log base 5 of x, etc. Right? So we want to derive and integrate all of these. But if you know how to do these are not hard at all. And then lastly, we do our inverse trig functions. Right? So sine inverse. We want to know how to integrate and derive, or how to do integrals and derivatives using this. Tan inverse, cos inverse. And like I said, these have a new name that you might not have seen in your 127 class. These are called, this guy's called arc sine. This guy's also called arc cosine. This guy's called arc. So we'll do our best to get through this in 4 days that we have. 4 lectures. We get as far as we get. So 5.1 is your introduction to the natural log function. So eventually we'll talk about deriving. Depending on what book you read, what mathematician you're talking to, there are different ways that you can define the natural log function and the natural exponential function, e to the x. There are different definitions, and at the end of the day, you can show that they're all the same. Larson chooses a common definition for higher level mathematics. It's not one that you would have seen in any other book. But it's cool. I like it. It's fun. So the natural log function is defined with this equation. Natural log of x is equal to the integral from 1 to x of 1 over t dt. only valid for x greater than 0. So maybe we'll talk about this for a little bit, but at the end of the day, ln x is ln x. It's a log function. It looks like a log function. But what does this even mean here?
It's equal to...
Like, how do you visualize, how do you think about the integral from 1 to x of 1 over t dt? Remember, we talked about these a little bit. These are called accumulation functions. And what this is going to calculate, what this is going to basically count, is the area under the curve of 1 over t. So this is your t-axis. What does 1 over t look like? It's got an asymptote at t equals 0. Kind of slopes down like this, right? So then the natural log function counts how much area you get under this curve from 1 to x. So here's 1. So however much area you accumulate as you go out to t equals x, this area here, that's ln x. So it just counts how much area you pick up as you move away from 1. If you move to the left of 1, that's okay, you can do that. Ln x will count this area, but it'll be negative. Why is it negative? Why is the purple area a negative area? Because the bottom limit of the integral is 1. Right? So if you do the integral from 1, and then you go to the left, that makes the area negative. Because you're going in the wrong direction. See, this derivative is not in any way, this definition is not in any way intuitive. But it turns out to be equivalent to any other definition you've ever had for ln x. It does tell you some cool calculus facts very quickly. Like, for example, so here's some facts about ln x. What's the derivative? The derivative of ln x should equal what?
1 over x.
1 over x, why?
And the accumulation.
So if you take the derivative d dx of an integral, this was what our second fundamental theorem of calculus allowed us to do. Right? When you take the derivative of an integral, you just plug in the top limit. So the derivative of ln x is 1 over x. That, if you remember nothing else from everything I put on the board today, you should remember that. What does this tell me about so the fact that the derivative is 1 over x, what does this tell me about the graph of ln x?
So decreasing.
Is the derivative positive or negative when x is positive? Positive. In this definition, ln x is only defined for x positive. So because x is positive, this derivative is always positive. Which means my function is always increasing. So y is always increasing. What would the second derivative of ln x be? How would you calculate it? You know the first derivative is 1 over x. which is x to negative 1. So what's second derivative, you can just use your power rule. Negative x to the negative 2. So negative 1 over x squared. So what's the sign of the second derivative always? Negative. If you plug in an x value and square it, well, x is always positive anyway, but the bottom here is always positive, the top's always negative, so my derivative, my second derivative is always negative. What's that tell me about my original function? Concave,
Down.
concave down. Right, negative is a frowning face, concave down. Okay, pretty cool. What's the slope of ln x as x approaches 0? Okay, more specific. As x approaches 0 from the right, as you put in numbers here that are getting smaller and smaller in the denominator, what is the whole fraction going to? Infinity. 1 over 0 is infinity, going to infinity. So the slope of ln x, as x approaches 0, the slope approaches infinity. So the slope of y as x approaches 0 is infinity. All right, last thing before I let you out of this hellscape. What's natural log of 1 according to this definition? How would I calculate natural log of 1 using this definition? Plug 1 in for x. So it's the integral from 1 to 1 of 1 over t dt, which is 0. You have no area. If you go from 1 to 1, you don't pick up any area. So I'm always increasing. I'm always concave down. My slope goes to infinity as I approach 0. And ln of 1 equals 0. So I can get a graph. So this accumulation function, the function that counts the amount of area under this curve, looks like, let's see. I know ln of 1 equals 0, so I have a starting point right here. Oh, let me do it. I know that I'm always increasing, and I know that I'm concave down. So here, this is always increasing and concave down. Why is this wrong? Yeah, my definition said that I have to have x greater than 0. So this isn't quite right, even though it's always increasing and concave down. So I have to use the fact that my slope is approaching infinity as x goes to 0. So I have to make this guy steeper and steeper as x goes to 0. This is ln x. It goes through 1, 0. It's always concave down, always increasing. So in 126, you actually define the natural log function as the inverse to an exponential function, but you end up with the same graph either way. You end up with the same function.
Here's 2.
What's that? So what, just to remind you, I'm not going to prove any of them because it's tedious with this definition, but what are your log rules? Remember your log rules? Those are going to come in handy. Like if you do natural log of A times B, how can you simplify or expand that?
Natural log of A times B.
So the natural log of a product on the inside becomes a sum outside. If you have a product inside a log, you can break it into a sum outside. If you have a division inside a log, what does that turn into? Subtraction outside. And if you have a power inside the log, so A to the B comes out front as multiplication. So it's B natural log of A. Okay, so we'll do some examples of these in a second, but this is just review. This is our graph of natural log x, so you're definitely going to want to remember that. The other thing is E. E is kind of funny using this definition. So remember, do you remember from pre-calculus what happens if you do ln of E? It's just 1, right? ln of E is 1. So the way that they actually define E in this book is they say E is the number that makes the area under this curve equal to 1. So E is the number that makes the integral, whatever number you can take to make the integral from 1 to E equal to 1. So here's 1 over T. Because my area is always increasing, and I start at T equals 1 having 0 area, my area is going to keep getting bigger, and as soon as I get to an area that's equal to 1, I'm going to call that number E. So as soon as you get this area in here equal to 1, the x value is going to be called E. Like I said before, it's not an intuitive way to define any of this. But so Larson does, and we can understand it because we know calculus. So E is the number that makes the integral on the area under the curve of 1 over T equal to 1. From 1 to E. But more practically, when you think of the number E, if you ever want to do a calculation with it, what do you approximate it by? Do you remember? 2.72, 2.718, 2.7. It's an irrational number. It goes on forever. It never repeats. I don't like that. But for us, we'll use 2.72 if we need to approximate. And then the only other thing we really care about is that if you take ln of E, you get 1. So in case, just like like every other time in this class, for every other chapter, for every other type of function, we like to have a picture in our head so we know what we're talking about. Okay? So if I write the function y equals negative 2 ln x, what picture should you have in your head? What does the sketch look like? So the original ln x, I have a picture for. Right? Ln x should very, very quickly be burned into your retinas as this picture. This is ln x. Concave down, always increasing, asymptote 0. Goes through 1, 0. So what is this negative 2 going to do to it? So because it's being multiplied, the negative being multiplied is going to reflect it, and the 2 being multiplied is going to stretch it vertically. It's going to double its vertical width. So something more like you flip it, and you stretch it out vertically. What's the domain of negative 2 ln x? Wait. I heard a lot of mumbles, but I could not interpret any of them. So the way regular ln x has a domain from 0 to infinity. The negative 2 ln x hasn't changed that. Right? It hasn't moved my asymptote over any. It's just flipped me. So the domain is going to remain the same.
Mm-hmm. Y equals natural log x plus 3. What's that graph look like?
The log, it's shifted over to 3.
Yeah, so you take your natural log x graph, which is increasing in concave down with an asymptote at 0. And because of the plus 3, which way do you shift?
Left.
You go in the opposite direction. You see plus 3, you shift to the negative side of the axis. So you go over 1, 2, 3. Which means your vertical asymptote should really be labeled now. I mean, I was not labeling it because it happened to be on the axis, but I should really label it. So at x equals 3, I have a vertical asymptote, and then I draw the same curve. Domain?
Negative 3 to infinity.
Domain, negative 3 to infinity. Right, we've shifted over 3 to the left, so my graph now cuts off at negative 3. So there's your graph of ln x. It's really pretty simple. It's only slightly more complicated than a line. That's got a little asymptote. That's about the difference. So this is a picture. These are the kind of pictures you should have in your head for natural log x. What about these log rules? Let's try to use some of these log rules so we remember how that works. So expand the expression.
I ask you to expand natural log of the square root of e squared minus 1 over e cubed, so the square root's over the whole thing. Oops, how would you do this? So expand means apply your log rules going to the right. Turn products into addition, turn division into subtraction, turn powers into multiplication. Yeah, so before you can get in here to the division, you have to get rid of this power of 1/2. So to expand this, you're going to take natural log of root e squared minus 1 over e cubed and turn it into this. Right, put the 1/2, put the square root as a 1/2 power. Then bring the 1/2 down. That's what this log rule says. If you have an exponent inside your log, you can bring it down in front. So this is inside of the natural log, it gets brought down in front. And then what can you do? Turn the division into subtraction. Now be careful, the 1/2 has to get applied to both, to all the whole result. And so this will be ln of e squared minus 1 minus ln of e cubed. Can I break up this ln of e squared minus 1? Make this ln of e squared minus ln of 1? No. You can't do anything with logs unless it's right here. Unless it's one of your log rules. I could factor this and break it up that way, but that's about all I can do. If I condensed, I get back to here. Condensing has to take a subtraction outside and turn it into a division inside. But I can simplify a little bit. What's ln of e cubed?
3.
So the 3 ln e, and what's ln of e? 1.
So it's 3.
So this is just 3. So it'll be 1/2 times ln of e squared minus 1 minus 2. Or if you multiply it out. Expand it. A nice, what you're going to see very shortly, even though you may not remember your log rules and you may hate your log rules, they save you from doing the quotient rule a lot when you're deriving. Right? If you have to derive natural log of some quotient, you can just apply your log rules and get rid of the quotient. It's much easier to derive something like this than to derive something like this if these were x's. So log rules are going to help make your derivatives a lot faster if you remember to apply them. So let me go the other way. Condense. Natural log, 2 natural log of x plus 5 natural log of y minus 3 natural log of z. I want to condense, I'm going to put these together into a single natural log. Yes, sir.
Does it matter which order you condense them in, from left to right or right to left?
Well, not if you do the right thing. The negative is always going to, the guy that's connected by a negative is always going to end up on the bottom. So, I mean, we can do it either way. As long as you follow the rule, you can do it either way. So for example, if you want to do it from right to left, first you have to put up all of the exponents, right?
Yes.
So this will be ln of x squared plus ln of y to the 5th minus ln of z cubed. And then if you connect these two guys, you'll get ln of x squared plus ln of y to the 5th over z cubed. because the subtraction turns into division according to this rule. And then if you turn this addition into multiplication, it becomes ln of x squared times y to the fifth over z. Or if you multiply that out, x squared y to the fifth all over z. So what happens if no matter how you do it, whatever has the negative in front ends up in the denominator, and whatever has positive coefficients should end up in the numerator.
So with the natural log being outside, would that be outside chain rule?
So that's what we actually care about, right? Derivatives. Thankfully, we know the derivative of ln x. Just by the definition, the derivative of ln x was super simple. Right? If you do ln x, you take the derivative, what do you get? 1 over x. By the second fundamental theorem of calculus, the derivative and the integral cancel, you just get the inside of that integral. So this is your rule. This is your only new rule for this section. And so basically, the calculus in this section comes down to exploiting this rule over and over and over and over. So a couple, maybe 2 quick examples, and then I'll let you go. So find the derivative. What if I give you something like y equals the natural log of x plus 7? What should the derivative of this be?
1 over x.
So the rule says you take 1 over whatever's inside if it's just x. Right? But technically, if it's more than x inside, you have to do a chain rule. In this case, it's a stupid easy chain rule because the inside derivative is 1. But you do have an inside and an outside here. So when you do the derivative of ln x plus 7, you start by doing 1 over x plus 7, and then multiply by the derivative of the inside, which would just be 1. So in this case, it didn't make much difference. What if I have a constant multiple, like y equals ln 3x? How would you do the derivative here? Y prime would be 1 over 3x, but then you have to multiply by the derivative of the inside. All right, you see the chain rule here? Derivative of natural log is 1 over whatever's inside, but then times the derivative of the inside. So it's just 1 over x again. Right? So multiplying natural log by a constant doesn't change its slope. That's one. I don't have to do the rest. C. What about natural log of x squared? Yeah, so if you do this using the chain rule, the inside is x squared, the outside is ln natural log. So the derivative of natural log is 1 over whatever's inside, times the derivative of the inside. X's cancel, right, because you got 1 on top and 1 on bottom. So 2 over x. How else could I have done that? Without using the chain rule, I can do this by bringing the 2 out front. You want to keep track of. Sometimes your log will simplify things quite a bit. Here, it doesn't make that much of a difference. But if you bring the 2 down in front using your log rule, then this is a constant multiple, and y prime is 2 times 1 over x. Okay, so I'll stop. On Wednesday, I'll do more derivatives, although they're not much more complicated. I'll do more derivatives and then we'll get into some integration.